but some cases it will be different, but maximum 100% condenser is a phase change type of heat exchanger. In phase change type of heat exchanger, the temperature will not change. Okay, now this is P5, then this is a pump. Okay, then after that it is coming to the pump, then the pump will pump again the liquid to the boiler. So this is how the reheat Rankine cycle is working. Now we will see the TS diagram for the reheat Rankine cycle, so that you understand. If you understand the flow diagram clearly, then you can make this TS diagram easily. Okay, so that you see the TS diagram. In the TS diagram, what they have given, first you take 0.6. So 6 is the liquid region, so that I have taken here. So that I am heating the liquid, it is converting into superheated steam. Then in 1 to 2 it is expanding. So expansion means entropy, isentropic process only. Okay, it is isentropic, so that's why S1 is equal to S2. Again what I am doing, I am heating this steam at P2 T2 into P3 T3. So what I am doing, again I am increasing the pressure, temperature equal to T1. Okay, then after that again from 3 to 4 it is expanding, so that's why this process is isentropic process, isentropic expansion, where S3 is equal to S4. After that the heat is rejected and steam is condensed into liquid at constant pressure. So 4 to 5 is constant pressure heat rejection. Again from 5 to 6 is the isentropic compression. So this is how I have plotted by understanding the flow diagram clearly, so that I can easily plot the TS diagram for the given condition. So based on that some of the numericals will come. So the formulas and all we will see while solving the numerical problems. But you understand how the reheat Rankine cycle is working and how the TS diagram for this. And I have told you one thing before I started discussing. So why this reheat Rankine cycle is introduced is to increase the efficiency of the Rankine cycle. How it is increased? You see this diagram, you take this is this area, you see, so that the area is increasing, so the work output is increasing. So when you increase the work output, what will happen? When we increase the work output, then the amount of, so the efficiency value will increase. This is how the efficiency is increasing. Okay, so the next one is regenerative Rankine cycle. So this is a regenerative Rankine cycle, but I have to draw the TS diagram in the outside, but I have occupied more space to draw the flow diagram, which should not be like that. Actually flow diagram is that only. I don't have enough space, that's why I have plotted the TS diagram inside this space. Okay, now you see this also same procedure, but something different. Okay, so here in the last case, that is in reheat Rankine cycle, what I have done, I have increased the work output to increase the efficiency of the system. Here I am decreasing the amount of heat supplied to the boiler to improve the efficiency of the system. Okay, now same concept, boiler is there. From boiler 1 kg of steam is going to the steam turbine. Okay, here there are two heaters they are using to preheat the water before sending into the boiler. Okay, so from this is a turbine, there are some two extractions before it is getting expanded in the condenser. Okay, now what is happening? So from this particular flow of the steam, some quantity of steam that I will take out at this point, that is point number 2. So 1 kg of steam is coming here. In 1 kg, m1 kg of steam I have taken here at point number 2. Then what will be the remaining in point number 3? If I take this much, then how much it will go there? 1 minus m1 kg will be remaining after this. So that 1 minus m1 kg or m2 kg of steam I am taking here. Okay, so I have taken m1 kg here, 1 minus m1 or m2 kg here, then what is the remaining will go to the condenser? 1 minus m1 minus m2 kg of steam will go to the condenser. Okay, so what I am doing, this point I will come after completion of this. So what I did, just you remember now, in the 1 kg of steam, m1 kg is already taken here, 1 minus m1 kg or m2 kg is taken here, then remaining how much quantity of steam is coming out to reach the condenser? 1 minus m1 minus m2 kg of steam only coming, that only going into the condenser. that much quantity of steam is getting condensed and converted into liquid, then again that is pumping. This is direct type of heater. Direct heater means direct mixing of direct contact type heat exchanger. Okay, so what is happening from here? The liquid is coming, that is the condensate water is coming, and it is going to this heater. What is happening? I am preheating the liquid here. Okay, so this liquid is coming here. Here already I have taken some quantity of steam. How much quantity of steam I have taken already here? M2 quantity of steam I have taken here. So from here M2 quantity steam I have taken, and here 1 minus M1 minus M2 quantity of steam is coming. So M2 plus M2 minus M2 will get cancelled. So here the water will get preheated at this point because steam temperature is higher than the water temperature obviously. Okay, so this temperature is getting expanded here, so that when it is expanding, comparing this temperature will be less. So at this point the temperature of the liquid will be low, and at this point the temperature of the liquid is increased. Okay, now here I have preheated some quantity of water. Okay, I have preheated to some certain level of temperature at preheater 1. Okay, or this you take as a heater 2. Then here how much quantity of steam is leaving? If I cancel M2, then how much quantity is remaining? 1 minus M1 quantity of steam will come out from this, then that will go to this pump where it will get pumped and it is going to the another heater. Now here 1 minus M1 kg of steam is coming inside through this way, and then water is coming through this way, and from the top side this M1 kg is available. So plus M1 minus M1 will get cancelled. Now 1 kg of steam will come out. Okay, that's why here 1 kg is coming. So now I got again the same value, 1 kg of steam. So here the water is again heated in the heater 1. Okay, how it is heating up? Because the steam temperature is higher than this temperature, so heat will transfer from here to this water. So now again I heated the water to some certain temperature. Now this water is coming to this pump, so that when it is coming to the pump, what I will do? I will pump it again to the boiler. Now you see, by using these two heaters, what is the use of these heaters? Sometimes only one heater will be available, sometimes two heaters will be available. So what is the use of this? So if I use this, I am just preheating the water before I am sending to the boiler. So what is the use of preheating the water? If I preheat the water, then I no need to supply more amount of heat to the boiler. So I can supply only little bit amount of heat to the boiler, so that it will be converted into steam, so that I can reduce the heat supply to the boiler to increase the efficiency of the boiler. This is how it is working. Okay, so for that purpose they have modified a little bit. Okay, so the steam is waste stream only. It's a kind of waste heat recovery also you can say. Okay, so by using this waste heat recovery concept, they have improved the efficiency of the Rankine cycle. Okay, now I think you have clearly understood the flow diagram and how the regenerative Rankine cycle is working. Okay, now the TS diagram you see, from 10 to 1 is the boiler. So 10 to 1 boiler, water is converted into steam. Then 1 to 2, what is happening? It is getting expanding from the turbine. So 1 to 2, that is the superheated steam is becoming dry steam after some expansion. Okay, the quality of steam is gradually decreasing from 1 to 2. Okay, then from 2 to 2, then 9, 2 to 9. So inside the heater also pressure remains constant, pressure is not changing. So 2 to 4 also, 2 to 9 constant pressure. So 2 to 9, 1 kg is coming, M1 kg I have taken. Then 2 to 3 also expansion in the turbine, that is also isentropic. Then from 3 to 7, 3 to 7 is constant pressure. So 1 minus M1 kg here I am taking. Then next 3 to 4. So from 3 to 4, this is 3 to 4. So from here to here also isentropic expansion only, that is 1 to 2, 2 to 3, 3 to 4. That is 1 to 2, 1 to 3, 1 to 4. Next 1 to 4. Then 4 to 5 is constant pressure heat rejection, 4 to 5 is constant pressure heat rejection happening in the condenser. Then 5 to 6, as we have already assumed in pump, the process is isentropic compression. So 5 to 6 isentropic compression. Then 6 to 7, what is happening? I am adding some heat, so that the temperature is increasing from 6 to 7. Then again 7 to 8 pump is there, so isentropic. Then 8 to 9 again I am heating, so heat is I am adding, so the temperature is increasing. then 9 to 10 again pump. So this is isentropic process. Okay, so that this is how you have to understand the efficiency improvement methods for Rankine cycle. While solving the numerical, I will tell you how to solve this problem. So that this flow diagram is important. If you understand the flow diagram, like in simple Rankine cycle we have derived the efficiency equation, likewise you can do for the reheat Rankine cycle and regenerative Rankine cycle also. Some basic concept if you understand, we can easily derive for reheat and regenerative cycles also. So this is the steam power cycles, that is Rankine cycle and modified Rankine cycle. Okay. Next, ideal gas and real gas. Okay, this is important topic. What is ideal gas and what is real gas? Okay, in the world we have to identify what is ideal gas and what is real gas. Okay, so first this you consider one container. In the container I am filling the gas. This we already studied in our schooling also. Okay, in intermediate, I think you might study about what is the ideal gas and what is real gas. Again I am just recalling it. I have taken one container. In the container I filled the gas, so that I can say the volume of the gas is equal to volume of the container, right? So both are equal, so that volume of container is equal to, here I have written, this is the one container where volume of gas is equal to volume of container. I can either say volume of gas or volume of container. Why? Because inside the container the gas is there, so the gas occupied the whole volume of the container, so that I can say volume of the gas is equal to volume of the container, right? Now I want to find out, so gases are made of so many molecules, so molecules, but in gases molecules are not closely placed, molecules are at some different distances. The distance between two molecules in gas will be higher than the solids and higher than the liquids also. Okay, so the molecules are not closely packed in gases, so you see this much distance will be there between one molecule to another molecule. So in reality, okay, there will not be any force of attraction. The force of attraction will be very less. Okay, the force of attraction for the gas will be very less. Suppose if you consider this thing, okay, I am talking about ideal gas. Okay, for the ideal gas the force of attraction between two molecules will be very less or negligible, and also if you want to know the volume of the individual molecule, okay, so this is the total volume of the gas or container. If you compare the total volume with the volume of individual gas, definitely the volume of the container or the volume of gas is much more higher than the volume of the individual gas or individual molecule. Okay, suppose I want to know the volume of the individual molecule which is present here. To compare, I want to compare the volume of individual molecule with the volume of the total container. So which one will be higher? Which is the volume of the container is much more higher than the volume of the individual molecule in the gas. So that if I compare, then I can easily neglect also the volume of the individual gas. So there are two conditions to prove the gas is ideal gas. The first condition is the volume of the individual molecule of the gas is negligible compared to the volume of the gas, the volume of the total gas. So, okay, if that condition is satisfied, then that is ideal gas. Then another condition is if there is no force of interaction between two molecules, then that type of gas is ideal gas. So that two conditions I have noted here. Volume of container is much higher than the volume of real gas, and another one is force of attraction is very less between individual molecules are negligible. If these two conditions are satisfied, then that type of gas is ideal gas. Okay, and one more equation also there for ideal gas. PV is equal to NR bar T or PV is equal to MRT. Okay, you can use either any of these two formulas. You can say PV is equal to MRT or NRT. So that this is the equation. If any gas follows this law, then that gas is ideal gas. If that gas not follows this equation, then that gas is real gas. Real gas will not obey this law. Okay, only ideal gas will obey this law. Okay. Okay, now I think you understand about what is ideal gas and what is real gas. Okay, again I will further define you more. Now we will see the compressibility factor. So what is compressibility factor? Okay, compressibility factor is the study of deviation of real gas from ideal gas. So what we have studied, ideal gas now we have studied, real gas we are going to study in compressibility factor. So ideal gas means there are two conditions for the gas to be ideal gas. One is it should be having very the volume of the individual molecule will be very less than that of the volume of the total container in which the gas is filled. And the second condition is what we have studied, the force of attraction will be very less between two molecules, that is ideal gas. Now compressibility factor is the study of real gas, how much deviation, suppose this is ideal gas and this is a real gas, how much the deviation real gas is there from the ideal gas, how far real gas is from the ideal gas, that we are going to study in compressibility factor. So it is a study of deviation of real gas from ideal gas. So for compressibility factor is denoted by the letter capital Z. The formula for compressibility factor is Z is equal to PV by nRT, PV over nRT. So Z is equal to always 1 for ideal gas. So if the Z value is equal to 1 means I can say PV is equal to nRT. That's why I got one idealized gas equation which we have studied. So if the gas which obeys this law, then that type of gas is ideal gas. So PV is equal to nRT is the idealized gas equation. If the compressibility factor Z is equal to 1, then it will obey then the gas will become ideal gas, then that is obeying the idealized gas equation. What is the idealized gas equation? PV is equal to nRT. Okay. Now we are coming to real gas. So in reality, how the real gases will become ideal gases, in which situation real gas is as ideal gas. So there are two situations in that the real gases will be, in most of the cases always ideal gas is not possible, real gas only available, but in which situation real gas will become an ideal gas. For that we are studying the compressibility factor. Okay. Now here you see there are two conditions, at low pressure and at high temperature. If the pressure of the gas is very low, then what will happen? Suppose I am taking one container. Okay. Now I am having like one engine cylinder I am taking, inside some gases are there. Okay. Now I am not applying any pressure on this. The piston is at the top level only. I am not pushing the piston towards downside. So it is not applying any pressure on that. If there is no pressure, if there is very less pressure, then you see the molecules will be, if there is no pressure, molecules will be largely placed. So the gap between two molecules will be very high. If the gap between two molecules are high, then there will not be much interaction or force of attraction between two molecules. When there is no much force attraction between two molecules, then that will be ideal gas. So at low pressure the gas will be ideal gas, and high temperature. So what will happen at high temperature? If I heat the gas, then what will happen? The molecules will move again further away. It will get more kinetic energy, so that the molecules will move further to some other distance, so that the distance will again further increase. So if the distance is increasing, then again the force of interaction will be less, so that in that situation also the real gas will behave as an ideal gas. Okay. Now this is also given in the graph also. So in the graph y axis I have taken as the compressibility factor Z, and x axis I have taken as a pressure. Okay. This straight line is Z is equal to 1. Okay. So the Z is equal to 1 is the ideal gas, and these curved lines all are real gases. It will be in real gas, and when it is reaching low pressure it will become a ideal gas. When it is reaching a high temperature it will become a real gas. So okay, this is about compressibility factor. Okay. Next, gas mixtures is the last topic in thermodynamics. So what is gas mixtures? Gas mixtures is usually a homogeneous mixture of different gases. It is nothing but so many gases are in the combined form, and that should not react with one another. That is the gas mixture. So if I mix one gas with another gas, there should not be any reaction between the two gases. That is called that type of thing is gas mixtures. If I mix some gases, that should not react with each other. So perfect example is air. In air we can say nitrogen available, oxygen available. Okay. So and also it will trace some argon, carbon dioxide also, so that even though air is containing this many types of gases in it, that one gas is not reacting with another gas, so that we are easily breathing and breathing out. Okay, so that air is the best example for gas mixture. Okay, and this is about gas mixture. So the definition is, it's a mixing of two gases and the two gases will not mix with, will not react with each other. If that two reacting with each other, then that is not gas mixture, then that will be composition or compound. Okay, that is compound. Okay, next some properties of gas mixtures also we have to see. In the gas mixtures, pressure of gas mixture, how to find out? There is one law, Dalton's law of partial pressure. What he is telling, if there is a gas in the container, so that we know in the container, if you fill the gas, there are so many number of molecules. If you want to find out the total pressure, though you can find out the partial pressure of the gases will be equal to the total pressure of the gas. So that total pressure P is equal to P1 plus P2 plus P3 plus P4 etc. the end. Okay, next, there are different type of gases are mixed together, so that you have to find out the total pressure in that. So the partial pressure of all the gases will be equal to the total pressure of the gas. Okay, total pressure, that is Dalton's law of partial pressure. Next, Avogadro's law of volume. There, if you want to find out the volume, so volume capital V is equal to V1 plus V2 plus V3. Similarly, how did you find the pressure of the gas mixture? Similar procedure we have to use to find out the volume of the gas mixture. Okay, this formulas you please note down. And temperature, as we already know, in any point if you take, the temperature will be remains constant only. The temperature will not be changing, so that the total temperature is equal to, if you take any point, at that point also the temperature, suppose there is one object, I want to find out the total temperature of this object. If I see the temperature this point and this point and this point, anywhere if I check, the temperature will be T only, it will not change. So the temperature will be always constant, it will not change. Next is specific volume. Specific volume formula is equal to volume by mass. Okay, so the volume by mass means there are n number of gases. So mass 1 is the small m1 is the mass of one gas, small m2 is the another gas. So if you divide the volume by the mass, then you will get the specific volume. Okay, so that if I want to simplify further, instead of writing specific volume, I am writing in the reciprocal order of the specific volume. So that in density, if I come in density, specific volume is the reciprocal of density. Okay, so that 1 by V. Okay, so what is the density formula? Mass per volume. Okay, so specific volume is reciprocal of density, that is capital V by M. Okay, now 1 by small v if I put, I will again rearrange the formula, which is M1 plus M2 plus M3 etc. by capital V, so that I am writing 1 by 1 separately. This equation I can split into 1 by V is equal to M1 by V plus M2 by V plus M3 by V plus etc. ME by V. So that is the if you take some reciprocal of this final equation, you will get the specific volume of the total gas. Okay, next one, density. So that, as we already told, density rho is equal to mass per unit volume. So if you want to find out the density, so that you can add all the gases density. So rho is equal to rho 1 plus rho 2 plus rho 3 plus etc. rho E. Next, internal energy. So internal energy M into UM is equal to this, and divided by M you don't take. Then here I am taking that internal energy is mass into that internal energy plus mass into second gas internal energy, then mass into second, third gas internal energy. Then I want only internal energy, so that you just divide this by M. Then if you divide it, you will get separately M1 by M into U1, M2 by M into U2, M3 by M into U3, like that. Okay, now I want to further simplify it, so that what I am taking, M1 by M is x1, so that it is x1 into U1, M2 by M is x2 into U2, M3 by M is x3 into U3, so that this is xe and ue, so that the total internal energy is summation of xe into ue, that is the formula. Next one, enthalpy. Enthalpy also similar procedure that we have to follow. How did we find the internal energy? Same procedure, M into H, then you will get the same. Like how did you find out the internal energy? Same procedure for enthalpy also. Next, entropy. In entropy we have to consider the number of moles also, so that entropy is equal to N1 into S1 plus N2 into S2 plus Ne into Se. So total enthalpy summation of total number of moles and total entropy of the system. Next, specific heat. there are two specific heat at constant pressure and constant volume. So this is the constant volume specific heat formula. This is constant pressure specific heat formula for gas mixture. Okay. Next, gas constant. Okay. Gas constant R is equal to R bar by M. Okay. So that R, if you want to find out the gas constant for the particular gas, then you have to divide that R bar is the universal gas constant and capital M is the molecular weight. So to find out the gas value, gas constant for the particular gas, then you have to use this formula, R is equal to capital R by M. While solving numericals we will understand. So with this topic we are finishing the thermodynamics syllabus. Okay, thank you.